You are watching Darasa Online.
The Darasa Online, welcome to our physics lesson. My name is Mr. Samuel John. Today we have a topic known as electromagnetism, but the subtopic is called magnetic force. And in this part of a magnetic force, we're going to discuss about the framing left-hand rule and the magnetic forces on a current carrying conductor and the magnetic forces between the two parallel straight conductors carrying currents. But if you remember, last time when we had the first part of electromagnetism, we talked about the current carrying conductor behaves as a magnet. When you have a wire, that wire carries current out of the plane, and we say that there is a magnetic line of forces which are moving around that. And for that case, we discussed about there must be the magnetic field created. And we saw the framing right-hand grip rule, which is used to determine the magnetic line of forces. Hence, we can determine the magnetic flux density, how they act. And from that point, we saw that you can have another conductor. So if this is the wire which carries current, that wire, it produces magnetism or magnetic field. If you bring another wire, here, this current may be in opposite or in the same direction. We're going to see that this wire, the second wire, will experience a force which has been created by the first wire. So our starting point now is, how do we determine the direction of the force which is acting on that conductor? We have seen that whenever we have a current carrying conductor, there must be a magnetic force around that. So the framing says that when the first three fingers of the left hand are held at right angles, so you have the first three fingers, these three fingers, if these fingers are held at right angles, it means the angle between the three fingers is 90. And such that this is the forethumb, which represents the magnetic field. This is the second finger, which is indicating the physical quantity, which here is the current. The thumb, which represents the force or the motion. When these three fingers are held at right angles, such that the forefinger is pointing in the direction of the magnetic field and the second in the direction of current, then the thumb will point in the direction of force or motion. So that is the framing left-hand rule. For example, those are the three fingers that you have. This is the thumb. This is the one which is indicating the direction of the fluid, which is the forefinger. This is the second finger. That is the thumb. So the physical quantities of the framing left hand is talking about the three quantities, like the current, fluid, and the force. Whereas the thumb is used to give us the direction of the force. When you have the direction of the magnetic field is known and the direction of the current is known, you can be able to find the direction in which the force will be acting. For example, let's go back to our diagrams here. So we have these diagrams. We know the direction of the current. And we say that if you, at this point, you draw a tangent line somewhere, of course you can find here, this wire is acting, it's a straight wire acting like that one. So the magnetic force is around here. So we have the second finger will be pointing in the direction of current. And the magnetic field is going in. And you can see how the magnetic forces will be acting. When you change the direction of the current, so the current is moving up. If you change the direction of the magnetic field moving down, so you can see if the current changes here, you must change the direction of the magnetic line of force. For example, if the magnetic force is applied maybe around this point here, you can change orientation of the fingers so as to find how the forces will be acting. So the main issues here is how to orient the three fingers so that we can know how the magnetic forces can be determined. Now, that is how the flaming left-hand rule can be used to determine the direction of force. But before we proceed, let's see now the demonstration of that force. And it has been found that experimental, this wire carrying current, it experienced that force which is proportional to the current. So when the current increases, the magnetic forces will also increase. And we saw that the magnetic force also depends on the magnetic flux density. And also it depends on the length of the conductor. So if you have a short wire, short conductor, the magnetic field will be affected and also the magnetic force. If you combine the three quantities, you have that force equal proportion to I, B, L. And this equals to I, B, L. We have a constant. So experimentally, this constant equals to 1. So the force, we normally call this as B. This is the force which is acting on a conductor, a straight wire like that. So we have the magnetic field, we have the currents, and we know the length of that conductor, so you can find the magnetic field. Remember, this is the maximum force which is produced. What do we mean by maximum force? Assume you have a wire resting on the field. This is how the magnetic field acts. And this wire is here. That wire is inclined here. The current flows like that, and it makes an angle theta with the plane. That's the angle it makes with the plane. So the angle between the conductor and the magnetic field is theta. And remember, when you're stating the framing, the quantities must be at right angles. So you can see here the current and the magnetic field, and of course, if you know the force where this B acting, suppose they're supposed to be perpendicular to B. And for the component of the magnetic field, which will be perpendicular to the length, so you should know that according to the formula, B is acting in the horizontal like that, current is given. The quantity that we normally change here is the length. The length of the conductor, which is perpendicular to the B, is not that. So you should find the component of this length. Suppose this is our length. So the component of the length, which will be perpendicular to B, will be given by L sine theta. This is the component of length, which is perpendicular to B. So applying the force now, force equals to B times current times the length. Since the length of the conductor, which is perpendicular to B, is not only whole length, but it's a small portion of the length, which is L sine theta, will be perpendicular to this B. So it's L sine theta. So we did this formula, and we come up with the conclusion that when the angle between the planes, when the angle between the conductors, maybe the conductor and the B, is 0, it means the conductor and the magnetic fields are parallel to each other. There is no force according to the framings. Here, when the angle is 0, the magnetic force is 0. And when the angle is 90 degrees, that's where the magnetic forces will be maximum. This will be sine of 90 is 1. So that is the formula that you did when you're deriving the formula for finding the magnetic force on a conductor. This is the, according to framing, you can have the maximum force or you can have the minimum, means 0, depending the angle the conductor makes with the magnetic field. So we know how to use the framing left-hand rule, and you know how to find the magnetic force on a current carrying conductor. This is the magnetic force on a wire, okay, a conductor which is carrying current. Now, suppose you may be having 2 wires, as we said before. When you have the wire carrying conductor as here, and you have another wire, there are 2 parallel wires here, carrying current either in the same direction or the opposite. That means one of the, from the principle you have seen that one of the wire will be behaving as generating a magnetic field. For example, the first wire here, it generates magnetic field, and the second wire will be found within the magnetic field which has been created by that. Hence, it will experience a force. Likewise, this wire also, if it's the one which is producing a magnetic field, the second wire will be found within the magnetic field which has been created by the second wire, the first wire. Hence, the magnetic force will be produced. It can have either repulsion or attraction, depending the nature of the current, how the current flows. Let's see now, how do you find the magnitude of the magnetic forces between 2 parallel conductors carrying current? To start with, let's have the first wire here. This is X. And then you have another wire, Y. Assume this is current 1, which is flowing on this wire. These are long wires. You don't have the length, they're long wires. And this is current 2 on wire, which is given the name Y. So there is a magnetic force within these 2 conductors. We don't know whether it's attractive or repulsive. We want to see. But let's see, how do we find the magnitude of the magnetic forces here? Assuming here the wire X is the one which is producing a magnetic field. Let's start here. We know that from this distance between the 2 is D. The distance between the 2 wires is given as D, or you can use any symbols. And let's find now the magnetic flux density at point P, due to the magnetic field which has been created by this here. Because of that, we have this wire produces the magnetic line of forces. And hence, how do you find the magnetic flux density at P, which has been created by this? So magnetic field, we know by the definition we did in the previous discussion, is given by mu I 1 over 2 pi d. This is the formula that we did in the previous discussion. The magnetic flux density of a straight wire from a point is given by mu I 2 pi d. D is the perpendicular distance between the 2 axes. So this is the magnetic field. Let's call this as the magnetic field 1. Why we call 1 is the magnetic field which has been produced by wire X. Or you can use 1 or you can use the X. Let's say X now. Wire X produces a magnetic field at that point P. Because of this magnetic field, wire Y will experience a force. That force is given by B. B, what is the? This is a magnetic force on wire Y. This is the magnetic flux density produced by wire X. Let's take it B1. What is I? We are looking for the magnetic force on a straight wire. This is our wire Y. So this will be our current 2, because we are talking about the magnetic force which will be experienced by wire Y. This is current 2, and this is the length of the wire. If it's a long wire, we talk of the force per unit length. If this length is known, we talk of the BI times length. So this is our question number 2. If you substitute question number 1 into 2, you find that the force on wire is given by B, which is given by mu I1 over 2 pi d times I2 And then sometimes we talk of force per unit length. So that is the formula. This is the force that will be experienced by wire Y due to the magnetic field which has been created by wire X. Likewise, when you consider, if you consider Y as the source of the magnetic field, you find the magnetic field of Y using the same current too, and you come up with the same formula that the magnetic force per unit length is given by mu I1 I2 over 2 pi d. And I said you can talk of the force if this length is given. If this is the long wire, we talk of the force per unit length. But we know if we are looking for the force on a particular wire whose length is given, it's mu I1 I2 times length over 2 pi d. Now, that's the magnitude. You are talking about the two parallel wires carrying current. They may be pointing in the same direction or in the opposite. Let's see. What happens? What is the direction of the magnetic forces between the two wires? Starting from the first wire, we know that the B produced by X will be extending up. This is that's where you can have a magnetic flux extending here, we know. So if you draw a tangent here, you can find the direction in which the magnetic flux density will be pointing. So remember, we draw a pattern, the magnetic flux density will be extending here. So remember, this is the straight wire. So why will experience the force? Let's see how this force will be acting. So this is the force on the wire. The current is moving upward. And you know the magnetic field is the magnetic flux density is acting into the plane. So here, into the plane. So our second finger, which will be the second, which is talking about the current here, will be pointing upward here, while the magnetic field is in. So here we have the current, and the magnetic field is in. So can you see here? If this is the case, the magnetic field at this point, current is up, magnetic field is on the plane, so the force created here will be pointing like that. If we change the orientation, so assuming that the magnetic flux density produced by wire Y will be found here, so we change the direction of the magnetic flux density, assuming that we are talking about this side here, where the magnetic flux will be pointing down. So we change the orientation of the current. Current is going up, and the magnetic field is, so you can see, the current is coming up, magnetic field is going down here. As we said, you can see from this diagram, but it's supposed to be like this. This is the current. This is the magnetic field is coming here out. If it's to me, it's coming here. So that is the direction of the force. So the force here will be acting there. And you can see from these two diagrams of the X and Y, there must be an attractive magnetic force between the two wires. So the conclusion is that the similar wires attract each other. So the current carrying conductors in the same direction produces the force of attraction. And you can prove when you have two wires carrying current in the opposite, there must be the force of repulsion. So our conclusion here is that we have the law of current. If you remember the law of magnetism, as we did in O level, it says that like poles repel each other and like poles attract. This is the law of magnetism. But don't talk of the law of current. When the currents are carrying conductor that moving in the same direction, the principle is that one, this is what like currents attract each other, while unlike currents repel. So like currents means currents flowing in the same direction, we attract each other. There must be a force of attraction. But the current moving in the opposite direction, there will be a repulsive force. So talk of attraction, or you can have repulsion force. Now, that's how you discuss about the magnetic forces. Now, not only discussing about the formula, but let's see how do we apply these formulas when solving examples. Let's see our example number 1. The question says, 2 straight parallel wires, they're given the names P and Q, are carrying current of 10 and 20 amperes respectively out of the plane and are 20 centimeters apart. From that point, you know that these 2 wires, they are not of a certain length. They are long. They are infinite wires. Step number 1, you should draw. That is example number 1. You draw the diagrams which shows the nature of the question. So you have 2 wires, P and Q. That's the information you have. You can be given. These are the letters P, Q, X, Y. But these are carrying currents. Current 1, let's take this current 1 here, is 10. This is current 2, is 20 ampere. And these 2 currents are out of the plane. So the current is taken out of the plane, is moving upward like that. And remember, last time we talked about the out of the plane. It might be out or down. And use the symbols. Sometimes we have these symbols, dot, and here. This is out, this is into the plane. So the 2 wires are given, the values of the current are given, and the distance between the 2 wires given. So the distance here, perpendicular distance here, is 20 centimeters. So step number 1, you should know the information which is given from the given equations. And those information should be shown on the diagram, label diagram. So we have wire P, Q, the current is I1, I2, and the distance between the 2 is 20. Now the question says, we have another wire, R, of length 15 centimeters. This time we have a specified length. But these 2 lengths here of the wire, the lengths of these wires are not known. So sometimes we normally extend up like that. These are the symbols in mathematics we normally use to indicate that these 2 wires, the lengths are not known. The length of this wire is not known. We talk about the infinite wires. But the 3rd wire, of which is given name R, it has specified the length, which is 15, and it is placed midway between the 2 wires. So we have wire R here, R in between, and its midway means the distance here now is 10, half of that, and the here is 10, half. That's the midway, half of the length. And the length of this wire R is given. The length of wire R is 15 centimeters. Now the question is, find the magnitude and direction of the force on R. Remember, we discussed about the forces which is acting on a conductor, and then we talked about the forces between the 2 conductors. But the question here is asking about the magnitude of the force which is acting on R, and we should know even the direction. But the current here is given. This current here, let's take this current 3, and it's given as 10 ampere. And this current is also out of the plane, like that. Now the question is, if you're looking for the magnetic forces here, since it is in between the 2 wires, you should start finding the forces produced by this force on wire P. There must be a force which is either attractive or repulsive. And then we have another force from this wire Q. We're going to see now whether it's attractive or repulsive. Let's find the force on R. Let's talk of force 1, which has been created due to the P. These 2 wires, they are parallel, and we have been told that this is the force on the wire. It's given by mu I1 and then I3. Since we know the length is L, 2 pi d. Let's find the magnitude, and at the end we shall find the direction. mu, this is 4 pi times 10 negative 7 times the I1 is 10, I3 is 10, and the length of this wire is 15. If you change, since at the denominator you have another length here, they cancel each other. 2 pi times d, which is the distance here, is 10. So there's no need of converting here into meter, because the centimeter we cancel out here. And we can find now the force which is acting on wire 1, R, due to P. We call this, the name of this force, as F1. This pi and this we cancel as give us 2. And we can compute that using your calculator. Even without the calculator, you can find F1 equals to, this 10 and 10 you cancel out. So you have 150 times 2, 300, times 10, negative 7. And this gives us 3 times 10, negative 5 Newton. So this is the magnitude of the force F1 on R due to P. Now, we are talking about the force. Because there are two forces here, let's see where is this force acting. We have seen that when you have two parallel wires carrying current, if these currents are flowing in the same direction, you can see the current is in the same direction. If you remember, the principle of the current, we say like currents attract and unlike currents repel each other. So these two wires are parallel and they are carrying current in the same direction. So there must be a force of attraction here. So this will be attracted here. This force 1 will be moving this direction. So it is a force of attraction. This force will be attracted. So our aim here is to find how is this wire R will be experiencing a force, either it's moving to that direction or this one. Because now is the one which is supposed to be discussing about. The main point is the force on wire R. If you're asking about wire P, that P will be moving to the right. But since we are discussing about wire R will be experiencing a force of attraction. They will be attracted here. And this will be attracted by this force, which is F1. And we'll be having another force here from P due to R. Now, how do you find R2? R2 is the same as mu I3, I2, the length. You're looking for the force on this R. So the length is given over 2 pi d. And this equals to 4 pi times 10, negative 7. I3 is 10. I2 is 20. The length again is 15 over 2 pi times the distance between them is 10. And you can see here there's some cancellation of the units here. And 2 pi we cancel out here. D by 1, 2. And we remain with F2. And this 10 we cancel out here. F2 equals to, this is 15 times 20 times 2. So you multiply, this will be having like 600 here, times 10 power negative 7. If you multiply, this is 30 times 2, 60. This is 15 times 2 is 30. And you can convert here. You can check the values here. 15 times 2 is 30. Times 2, this will be giving us 120, I think. Check your calculator. If you multiply by that, how much do you get?
You are watching Darasa Online.
If you don't have a calculator, you can check by roughly arithmetic. This is times 2 is 30. 30 times 2 is 600. So this is what? 600, and they convert equal to 6 times 10 negative 5 Newton. So this is the force which is acting on R due to Q. And we have seen that the two wires are parallel. And again, the force on R, we are looking at the force on R, not on Q. The force on R due to P and Q. So this will be experiencing another force, F2 due to Q. It will be attracted toward the coil Q. And you have seen two similar wires carrying current will be having some sort of attraction. So this will be attractive force. So on this Q, and there will be attractive force on that. And the net force here, you find, is the summation of the two. Because now the two forces acting in opposite directions, you find the one with greater magnitude. So the net force equals to, our first value was 3 times 10 power 5. And you can see one is pointing the other direction. And this will be 600, which is now pointing to the right. So we choose this will be a negative now. Since it's moving to the other side, this is 6 times 10 negative 5. When you're finding the force, you're supposed to consider the sign. We choose the positive direction where the force is acting here. And that one will be negative. So the net force here equals to 3 times 10 negative 5 Newton. And the direction of this force will be to the right. Or we say toward wire Q. So remember, that was our P and Q. So that force, the net force will be moving to the right, or this wire which is in the middle will be drifted toward the Q. So that's how you can find the direction of the magnetic forces as well as the magnitude of the force acting on a certain wire. Now, this is the example number 1, where you can be given a question like that. So you have 3 wires, and you are looking for the magnetic force on a certain wire which is in the middle, or between the midway of the wires. Let's see example number 2. Our second example is talking about, we have a copper bar. It's a copper, it can be aluminum. These are of certain length. It's given, the length of that wire is given. And that wire X is resting on 2 copper nails. So now the copper nails are 5 centimeters apart. In other words, that's the length of the bar X. In other words, the length of the bar X is known. Now, if that X is resting on 2 bar of copper, and these copper nails rays are connected to a battery so that it can take the currents through wire X. And the current is given as 4 ampere, and it is moving in the anticlockwise manner when the switch is closed. Before we proceed, let's see now the question. The nature of the question is, you can draw that question here the way it's given. It can be a horizontal, it's on a horizontal plane maybe. These are 2 bars. Okay, they must be of the same maybe. You know. These are 2 bars of copper, and we have these are rays of copper. We have these are like metals. We have a certain material which is given now resting here. The X is resting on the top of this another copper materials, and the distance between the 2 is given as 5 centimeters. And the question says now, there is a connection. So if in order to connect a battery, you must connect a source, maybe a wire. Something, otherwise be more like that, and then it must be a wire. We are told maybe this is a switch. The switch. And the current is supposed to be moving anti-clockwise, so this way. Okay, if this is the case, our battery will be like that. So the current, when the switch is closed, the current will be moving this way. And then coming here, here. That's our current. That's our anti-clockwise. So from this diagram, you can be able now to see that when the current flows through this main switch, through the wires, and then coming to these copper materials, now this side is open, so the current will be coming down to this bar X, and then going around a loop.
You are watching Darasa Online.
Now, the question is, on this part, we are told the magnetic field is 0.1 and is acting perpendicular to the plane. So we draw, remember, we normally draw this. We know how to represent this one. We said B, when you see X, that's the magnetic flux density is pointing into the plane. The second part of this question here, the second part, now let's see the questions. Now the question says, part 1, A, state the direction in the bar, state the direction in the bar in which bar X will move when the switch is closed. State the direction in which bar X will move when the switch is closed. Okay, when you close the switch, according to the principle that we have done with the framing left-hand rule, that the current is known, how the current flows, and the magnetic field is pointing into the plane, and you are supposed to find how this Y bar X will experience the force. So from here, if you use framing left-hand rule, so the current is moving down, and the magnetic field is pointing in. So you can see here, current, the second finger current, and the first finger will be pointing to the magnetic field, which is given as 0.1, but it's pointing in the plane like that. So you can see the thumb is pointing to the direction in which the force will act. So here, our force will be acting to the right. So part A, the force will be acting to the right, as shown in this diagram. Part B, calculate the angle to the horizontal at which the rays must be raised. These ones, you raise them up. They are horizontal here. If you can see this diagram here, we have two rays right here, the way they are pressed, and we have another bar on top. So you lift them certain angle, and when you lift the angle, when you lift them up, the angle will be increasing somewhere. Sometimes if you don't find that angle, it will reach that this bar will slide down. So looking for the angle at which, when these rays are lifted up, the bar X will remain stationary. And we know that the mass of that bar is given, and we are told that the direction of the field remains unchanged. So now let's go back to the formula. In mechanics, we talked about this inclined plane here. In mechanics, inclined plane, we had an object which is resting on inclined plane here. That is of M. We know this component is mg cos theta, and we know that's RW reaction. So now, and this one is mg sine theta. So these are the component of the mass. We know that when you have an object like this one, when you has been lifted up, so initially the angle between the rays and the horizontal is 0. So when you are lifting them up, you are making an angle theta with the horizontal. So we are told the direction of the magnetic field remain constant. Initially, the magnetic force was acting to the right, horizontal. So let's check this is our direction here. The force was acting horizontal like that. So you must also now resolve this force so that to rebalance the mg sine theta. It's the one which will determine whether the part will be sliding down. So this first force here is isolated. So we're supposed to find another force which will be balancing this, and we make this particle, the bar X, not to slide, and it remains stationary. So this angle here is the same as theta. So if we resolve that force here, we find that the component here will be F cos theta. The component of that force along the plane will be F cos theta. And from the principle of mechanics, that's how you can resolve. So from there, we are told that that x per x will remain at rest. So the forces that we make this will remain is the 2. So the mg sine theta equals to F cos theta. So mg sine theta equals to F cos theta. But we know this F is the force which is acting on a wire, or which is by x, is given by B current times the length. So we have mg sine theta equals to B L cos theta. Our aim is to find the angle. So you can find anyhow. Arrangement of these trigonometric ratios, you can find, we know tan equals to the sine of the angle over cosine. So if you look from this equation here, if you divide it by cos, you come up with the concept of tan here, cos theta, then cos theta. This we cancel out, so we have mg as we defined there is this will be tan theta equals to BIL. And mg, you can divide it by mg on both sides here. You can find that tan theta, which is the angle, is given by BIL over mg. So you know the value of the magnetic flux is given as 0.1, and the current was given as 4 ampere. Length, I said that length was 0.5. Is what the length was 5 centimeter. That was the between the rays. That was the length of the bar x. So you convert this into 0.05 meters divided by mass of that bar is given as 5 gram. 5 times 10 power negative 3. And this is, our G is 10. Try to check the values there using your calculator. Plug the values and check how much are you getting. Okay. Now, using your calculator, you can find out what is the tan of this theta. But here you can see tan of that angle here equals to, if you make, this will be 4 times 10 negative 1. This will be 5 times 10 negative 2 divided by, this will be 5 times 10 negative 2 here, using your mathematics, negative 2. And these 2 negative 2 we cancel out here, very easy, and then this we cancel out. And then we left is 4 times 10 negative 1. This equals to 0.4 tan theta equals 0.4. Check your calculator. Now, you're looking for the angle. So, using my calculator here to find the at angle, you're supposed to find the tan inverse of 0.4. That will give us the angle at which those rays must be raised. Tan inverse of 0.4, let's check together. Is 21.8. Okay, that is the angle at which the bar must be raised so that the bar x should remain stationary. So can you see that question? It's very interesting. It is connecting mechanics and electromagnetism. So you might be given a question of that quality where you're supposed to apply different concepts, resolving the forces so that we come up with the final questions. Now, after these 2 examples now, I think now you can try this question as an assignment. This is your assignment. Let's now check if you can do. The question is given as we have a wire Y, which is a long straight conductor carrying a current of 5 ampere, and you are told is out of the plane. And that is a wire Y. And then you have a rectangular loop ABCD of dimension is given. The dimension of that loop is given. That is the length is 10, the width is 3 centimeter. These are dimensions. Now, that loop is suspended with its long arm parallel to the conductor. Think about that. You should know how to draw these two scenarios. We are given the first wire is given a straight conductor. Now it carries current out of the plane, and then we have another conductor which now is forming a loop, ABCD, a rectangular loop. The length is given and the width is given, and the current there is given as 3 ampere, which is flowing clockwise. So let me give you the hints on how to check and solve those questions, but it's your assignment. If you are given such question, step number 1, you draw that wire Y. As I told you before, that wire is given as the name. Long straight wire is infinite wire. It carries the current of 5 out of the plane. So you should indicate the current direction of this wire as 5 ampere. And then, and that is the wire Y. And along this wire Y, you have a rectangular loop. It's given a rectangular loop which is closed here, which is given, the dimension of that is given, is the length here is given as 10, and this width is given as 3 centimeter. But you are told this, the long arm here, this the long arm, is parallel to Y. You can see it's parallel to Y, and the distance from that parallel wire, the 2 parallel wires here, is given as 2 centimeter. Very important. The 2 centimeter is the distance between the long arm and the Y, which is now a straight long conductor. So the 2 wires, they are parallel. These 2 are parallel, but the question says here, it's where it's given, the current in the loop is clockwise direction. So it's moving like that. You see? So we are forming a loop. A, B, C, D. Now, the question is asking about find the magnitude and direction of the net force acting on this loop. The magnitude. So where do we start? We know that we are supposed to talk about the loop AD, this A, B, D, C, D, A, B, C, D, but we know the parallel sides. It's to talk of the wire Y and this part AB. And the distance between them here is 2. You find that force 1 on this. So now you have seen that this is 2 parallel wires. There will be an attractive force. That force will be acting there. So we find that force as mu I1, maybe this is I1, this is I2, maybe you can choose this I2. According to the question is given as 3. So I1, I2, because the length of this side is given, we talk of that 2 pi d. And so you find that force, F1, as part of your assignment. Now you can do that one. So you find mu is given, I1 is 5, I2 is 3, the length is given as 10, and you find the F1. Then F2 is the force which is acting on part of a loop, which is now given the name BC. BC. So consider this is Y, and the BC is here. BC. The distance here now is from Y is 2, 3, 5. This is current is moving up, I1, the same current, but this time the current is moving down, I2. This is 3, this is 5. Now, because we have seen these 2 currents are moving opposite, there will be a repulsive force, that is F2. F2 is moving to the right, F1 is moving to the left. And we find the magnitude of that force equals to mu I1 I2 over 2 pi d. What changes here is the distance between the two. This is 5 and this is 2. After finding the magnitude of the forces, and you can be able now to find the net force here. I say this is here. I'm giving you the hints on how to go about. You find F1, you find F2, and you can see F1 is pointing to the left and F2 is pointing to the right. Now, which one is greater? By mathematics now, we have this, a small distance produces the greater force. So it will be F1 minus F2, and that force will be moving, pointing to the left. So why do you choose F1? Because the distance here is the one which determines the magnitude. We have a shorter distance. This is 2. This distance is 5. So the greater force is F1. When you find the difference, you get the net force. So that's the end of our presentation. I think you have enjoyed. So you have seen now how to apply different techniques when solving equations involving electromagnetism. In the first part, we talk of the magnetic flux density. In the second part, we talk of the magnetic force. And it's my hope that at this point, you'll be able to solve any question involving magnetic force and the magnetic flux density. Keep in touch on Darasa. As you can see, more programs are coming. Goodbye.